Yeah, I think it's just a video.
Everyone, welcome to the session on ML sparsity and dynamic shapes. I'm Roshan Dathathri from Microsoft Research. We have 4 talks in this session, and it's my pleasure to welcome Guan from Shanghai Jiao University to present his work on Fractal, which is a joint multi-level sparse pattern tuning of accuracy and performance for DNN pruning.
Thank you.
Always.
So hello everyone. This is Guan from Shanghai Jiao University, and I'm introducing our work Fractal. It's a joint multi-level sparse pattern tuning system of accuracy and performance on the deep neural network pruning. Okay, so this is a plan of my talk, and I'm starting from the motivation of sparse structured patterns, and I'm going to our pattern IR design, which is a general representation for the pruning patterns. And I will introduce our tuning system Fractal, and finally I will evaluations. So the motivation of pruning is very simple. As we all know, the DNN models are scaling very fast, rapid, and recently, and the model size are grows very rapidly, and the cost is very expensive. So we all know that model compression is needed, and for model compression, we have many methods. For example, we have quantization, which aims to use less numerical precision to represent the values in the network, and we have pruning, which is fewer connections in the network, and we also have distillation. We try to use a smaller model to get the same performance, and also many other methods. And in this work, I'm focusing on the model pruning. And for deep neural network pruning, the idea is we have a trained dense model, and we remove some of its connections to get a pruned sparse counterpart. And we fine-tune the model with extra data for extra epochs to get a fine-tuned version, which can alleviate the accuracy degradation from the pruning. And by pruning the network, we can have less memory footprint and less computational complexity. And one thing is very important in neural network pruning is the accuracy and performance trade-off. And I borrowed this figure from Professor Hoffler's survey. And there are 3 regions in the trade-off of network pruning, which is the zone A, and where the accuracy is quite good. However, with the low sparsity, we get less optimized performance. And in zone B, as the sparsity gets so higher, we get acceptable speed up. And however, the accuracy is also good. And finally, in zone C, with the relatively high sparsity, the accuracy start to drop. So we have to find the maximum sparsity we can get without accuracy loss. And on modern hardwares like GPU, sparsity is not a friend of them because it has random memory access and less compute intensity. So in this graph, we can find that we have to get over 99% sparsity to beat the dense baseline. So one solution is to use the structure pruning patterns. That means given the tiled kernels on GPU, we can prune the weight parameters according to some tiled structure. For example, we can prune the whole column together to get the column-wise pattern, and we can prune the block together to get the block-wise pattern. And similarly, we have tile-wise pattern and the vector-wise patterns. And to design the structure pattern, it is important for us to maximize the hardware performance and alleviate the accuracy degradation. So the current sparse patterns are delivered as different sparse operator libraries, and they may have different networks and operators and backends. And currently, this sparse operator letters often just support some of the backends, but not all of them. So this is the current scenario of how we're designing a pruning algorithm and the corresponding sparse operator library. And so the idea is we can use a tuning system to select the optimum pattern automatically and generate the efficient sparse operator. To design such system, the first thing we have to do is to get a general representation for patterns. So this is our proposal, that is pattern IR. And the idea is very simple and generates from the loop perforation idea of approximate computation. So suppose we have a tensor here, which is two-dimensional, and it has I and j axis. And if we want to have it pruned column-wisely, so we can use the loop perforation idea on the I-axis. And for example, we're using 50% sparsity here. So we have the indices for the I loops, which is 1 and 3 remained, and the 0 and 2 are pruned. So the loop is transformed to some sparse fashion, and we can construct the column-wise pattern accordingly. With this idea, we can get a general representation for the structure patterns. It is based on the loop hierarchy and perforate some of the loops from dense to sparse. And in this representation, we have the loop name, which is simply the access name, and we have the dependency according to the order in the representation, and we have their non-zero elements, which is labeled on the as the superscript, and we have the full length of the loop, which is as the subscript. And here I show some example of the previous human design pattern that is expressed in this pattern IR. For example, for tile-wise, we have I4 and the J0 is 2, 1 and J1 is 2. And similarly, we have VW and the BW. So generally, all the existing sparse patterns can be represented similarly. And which is more interesting is that we find that with this representation, we can even design some new patterns that is not discovered by the developers yet. For example, we can combine TW and VW together to get the hybrid patterns. And to actually get the efficient operator, we have to generate the operator code. So here is how we parse the pattern IR. So given the pattern IR in the middle, as shown in the circle number 3, we can transpose it to the underlying storage. For example, for the sparse loop J0, we store the full values for it and the indices, which is attached to the loop. And accordingly, we can get the sparse loops on the right-hand side. And given this pattern IR, it is represented as a BW pattern on the left-hand side. And furtherly, suppose we want to bring this BW pattern into more fine-grained structure, we can further prune it with horizontally tile-wise patterns, and this will give us another 2 levels of pattern IR, which is the I1 and J1. And here the I1 is sparse, which is from 4 to 2, and so we have more fractal ELL storage for it. It is stored in the left-hand side, and accordingly we have the corresponding sparse loops. With this pattern IR, we can build our pattern tuning system, which we call it Fractal. And to start with, we can generate many pattern IR candidates as our search space. And we first use an operator pruner, which is the existing pruning algorithms. It generates the sparse mask, and we use it in the DN model to evaluate its pruning loss as some matrix. Nextly, we will use a code generator, which is existing sparse compilers, and we generate the sparse operator and evaluates its actual latency on the backend. And with this matrix, the sparsity matrix and the actual latency, we can find the optimum pattern by selecting with threshold. And to accelerate the searching process, we use a cost model to evaluate the actual latency instead of generate all the operators. And we also have some configurations for the tuning process and also the tuners. And to be more specific, I show an example of how we generate an actual operator. Here is the dense operator. And first, we generate the pattern IR candidates, which is represented as some primitives, including the toggling ones and the perforation ones. And it is parsed into the sparse expressions with the sparse axis, the sparse buffer, and the sparse iterations. And then we further lower it into its dense format, which is expressed in existing operator libraries. And finally, this dense operator is tuned with the sparse compiler. And finally, I will show our evaluation results. And in this graph, I will show SPMM operators with different sparsity, like 50%, 75%, and 93%. And we benchmark with different pattern, existing sparse pattern libraries like TW, BW, and VW. And let's start with the shape of 1024, 1025, 1024. As we can see, the fractal reaches good results and speed up compared to different baselines on this shape. And similarly, for other operators, we can have a consistent speed up on the shapes we evaluated. And for as we can generate the code automatically, so we can connect to different backends and generate efficient code. Here we evaluate our result on A100 Tensor Core, A100 CUDA Core, and also RTX 180 GPU and also CPU. As a sensitivity study, we also show our trade-off frontier that evaluates the pruned accuracy on actual network and the end-to-end, the actual speed up of the model level result on bird pace and bird large. As we can see, Fractal pushes the frontier dramatically compared to existing works. And the layer one is how we discovered the actual discovered optimum sparse pattern for each operator in the actual network. We can find that we find totally different and even new patterns for some of the operators. And that's all. Thank you.
Thank you. Any questions?
When you do some kind of structured sparsity, and you need to read the information about the structure too, which can be considered as metadata, I guess.
Yes.
Does that have any overhead? I mean, does it consume any extra memory bandwidth on top of reading the elements?
Yes. Because after pruning, the value data is compressed. However, we are introducing extra storage for the indices, like showing here. So for the values, we can reduce it like according to the sparsity. However, we're using extra storage for the indices.
Oh yeah, I was gonna ask like, is that significant or something like we can ignore? Did you do an analysis on that part? I wonder.
This is actually according to the pattern and sparsity. For example, if you are pruning like up to 90%, so you only have 10% of the values remaining, and you only have 10% the same amount of indices, so which is like 20% of the previous value.
Oh, so okay, so you store indices explicitly.
Yes.
I see. Okay. Yeah, good work.
Thank you.
Any other questions?
Thank you for the good talk. And I have a question about the search space. So we know if we want to tune a kernel such as MATML, it requires about half an hour for TVM on current GPUs. And for this work, I think the search space is really large, since there is a space of the sparsity patterns and the space of the sparse kernels. So how long does it take to find the optimal solution, optimal plan for a model, or are there any techniques to solve this problem? Thank you.
Yeah, thank you. This is really a big problem of our work, and because we don't really show the detail of the pattern IR tuner here, and which is in our paper, you can check it. And generally speaking, we have many ways or methods to reduce the search time. For example, we're using the cost model here. Sorry, let me get the laser. So if we are using the code generator and tuner, it may cost a lot of time. And so we add a cost model here to get the latency directly. And the cost model, we're using a ML-based model. And this is one way. And in the tuner configurations, we're setting a threshold during the tuning. For example, if you find that the operator is less prospective in the early stage of tuning, we early stop the tuning and just go for another candidate. So for example, if we are tuning for a certain operator, and it may take, for example, 20 minutes, and after 2 minutes of initialization phase, we find it less prospective, so we start the tuning.
Thank you. Let's thank the speaker. Is Wayne you here? Okay, so the next talk will be remote. Feng will be presenting their work on optimizing dynamic shape neural networks on accelerators via on-the-fly micro-kernel polymerization.
Today I want to show our work optimizing dynamic shape neural networks beyond the fly level polymerization. Nowadays, dynamic shape neural networks gaining popularity in emerging intelligent applications to tackle complex tasks. For instance, in natural language processing, models use variable input sets based on the sequence length, leading to tensor operators with varying shapes. However, introducing dynamic characteristics in tensor computations raise new challenges for performance optimization in libraries and compilers. While library interplay includes several effective operator implementations, especially optimized for widely used shapes. Well studies reveal that the carefully designed specific operator implementation is highly suitable for all shapes, resulting in suboptimal performance inevitably. For example, we observed that the gene routine provided by Huimin has significant performance violations for different material shapes, even if both shapes are compute-bound. Studying shape tensor compilers in that tensor in the PVM tensor operators and searching through value structures within the substantial search space to determine the optimal implementation in deep neural networks. Initially, the neural tensor program with a fixed shape is represented by a three-dimensional nesting loops. Next, a static shape tensor compiler transforms the tensor program into a tile tensor program, computing the index. After that, static shape tensor compiler exploring optimal tile size within a extensive search space. Ultimately, a function the tensor program related to the static shape in direct. This static shape tensor compilers often demand significant time to generate efficient implementations for operators with predetermined shapes. Consequently, the time-intensive method employed by static shift tensor compilers is unsuitable for dynamic shift scenarios. The dynamic shift compiler based on shift range, such as Dathathri, generates a series of high-performance tensor programs by using hence schedule calculator to define shift range. During runtime, the shift pre-compiled tensor program is selected based on the non-associated built-in costly compilation space. Existing static and dynamic shift compilers optimize tensor operators for specific interval-range, leading to potential performance degradation or runtime errors for out-of-range shifts, as well as suboptimal performance for in-range shifts. Thus, effective mechanism is required to deliver high-performance tensor programs with actual shifts. We introduce the two-stage optimization approach based on micro-kernel polymerization and at delivering high-performance program implementations for arbitrary shifts. Micro-kernel operates in two stages. In the organized stage, micro-kernel creates a set of highly optimized micro-kernels along with performance models developed from micro-kernel templates using auto schedulers. In the online stage, upon running the runtime shift, the micro-kernel dynamically adapts its programming template into various string implementations through polymerization patterns. Ultimately, the optimal tensor programs for the non-shift is selected and executed, determined by accurate and elaborate cost model. Poly comprising two stages: micro-kernel generation, micro-kernel polymerization, and multi-level accelerator abstraction. Multi-level accelerator abstraction incorporates multiple processing engines, electrical memory, including local memory, into a single processing engine, and global memory shared among multiple processing engines. This hardware abstraction allows Minyi to seamlessly adapt to different accelerators that NVIDIA GPU can carry NPU. They utilize a micro-kernel template, which is derived from the organics and organized for efficient use of local memory. For each micro-kernel template, we generate a collection of fixed-size micro-kernels by using static shift code schedulers, such as TM. The performance model experience. We organize online books using predefined polymerization patterns to structure templates into different programming implementations for the underlying operator. We utilize the following function model to estimate the execution cost of the programming implementations. The function model consists of two parts, namely function weight, which represents the number of weights needed to execute all pipeline tasks in parallel, and the function which is used to estimate the cost of executing the pipeline tasks. Our experiments conducted on GPU and the NPU platform use thermal libraries and baselines to evaluate the acceleration effects of Minyi on operators and networks. The results show that Minyi significantly accelerates the execution of dynamic shift operators. The GPU platform multiply achieves a average change speed of 1.47 times compared to index. Average convolution speed up of 1.98 times compared to Jingling. On the NPU platform, usually achieves average speed up of 1.10 times for G and 1.41 times for convolution. It effectively accelerates the end-to-end execution of dynamic shift DNN. Typically, achieves average speed ups of 1.39 times, 1.38 times, 1.36 times, and 1.37 times for birds. Digital birds, respectively. For AlexNet, GoogleNet, RedNet, and Minyi, Micro-Kernel average speed ups are 1.34 times, 1.69 times, 1.59 times, and 1.22 times, respectively. Compared to solar approaches that bear out, Micro-Kernel demonstrates superior performance, achieving average speed ups of 1.94 times for G operators and 1.55 times for NLP models. Furthermore, Micro-Kernel improves its flexibility by effectively handling various shape ranges. We employed Llama 2 from Huimin for evaluating both operator and end-to-end inference performance. The results indicate that Micro-Kernel effectively enhance large language models, yielding average speed ups of 1.16 times for operator performance and 1.03 times for auto inference. We propose a two-stage optimization approach founded on Micro-Kernel polymerization and introduce a preset yet lightweight cost model that facilitates additional polymerizations. Experimental results demonstrate the effectiveness of our approach, achieving an average speed up of 1.49 times over window race of representative acceleration. Thank you. And any questions?
Thank you. If you're online, can you unmute yourself? Hey, thank you. Any questions of Feng? Feng, have you compared your approach with auto-tuning works like TVM? What kind of speed up can it give? Auto-tuning compiler works which use static shapes.
In the offline, we use the approaches like the TVM to find the micro-kernels.
Not that audible, actually. I think there's probably some disturbance.
Can you say again? The network is poor.
No, go ahead.
I don't hear your questions. The network is poor. Can you say again?
Yeah, let's try one more time. I'll repeat my question. So
Okay,
there are
okay.
compiler works like TVM which use static shapes and auto-tuning to get a good static shape, right? So a static shape. Have you compared against works like that? Have you evaluated your approach and seen? Have you evaluated their approach and seen how much performance benefits your approach gives?
Did you mean did you mean compare our approach with the static shape comparison?
Yeah. Yes.
No, we don't do that experiments. Yes, this is a good question. But the static shape compiler is focused on static shape things. So we not choose the static shape compilers as the base stack. We chose the Fendo library and the dynamic shape compiler as our base stack.
Yeah, no, I understand that makes sense because having static shapes have their own overhead, but I wanted to see what is the performance difference like. But that's fine. That makes sense.
Okay, thanks.
Any other questions? Okay, thank you, Feng. Thank you for being online.
Thanks. Thanks.
The next talk will be from Ruibo Fan, and they're from Hong Kong University of Science and Technology, and they'll be presenting their work on DTC-SpMM, which is bridging the gap in accelerating general sparse matrix multiplication with tensor cores.
Hi everyone, it's my great honor to introduce our latest work on enhancing the performance of sparse matrix multiplication through the use of tensor cores. This collaborative effort is from the Hong Kong University of Science and Technology, the Guangzhou campus and the main campus. I'm Ruibo, a PhD student from the Data Science and Analytics class. Let me first introduce some background information. Sparsity is natural in numerous real-world applications, including scientific computing applications such as the fluid dynamics and circuit simulations, as well as many machine learning applications like graph neural networks, the mixture of experts, or the support vector machines. Well, sparse matrix multiplication, SpMM in short, is a pivotal operation within these applications, where a sparse matrix A is multiplied by a dense matrix B, resulting in a dense matrix C. SpMM is more computationally efficient and has a smaller memory footprint compared to the general matrix multiplication, the GIM in short, making the optimization of SpMM a focal point in recent research. From a hardware's perspective, recent NVIDIA GPUs are equipped with tensor cores, which are advanced matrix computing units capable of delivering significant performance improvements over traditional CUDA cores. However, previous research has concentrated on the common CUDA cores, and there is a significant challenge in aligning the irregular patterns of sparse computation with the regular computational patterns that the tensor cores are designed to handle. Well, TCG pioneering work presented at ATC-23 is the first to utilize tensor cores for accelerating general purpose SpMM. It introduces several key techniques such as dividing the sparse matrix into small-scale TC blocks, which matches the shape that the tensor cores supported, and employing sparse graph translation to shift the condensed matrix to the left side. And a novel storage format is also proposed for representing the condensed matrix. The TCGM's algorithm's workflow is similar to the T-spaced GM, with one CUDA thread block being responsible for all TC blocks within a single row window. During each iteration, the CUDA thread block performs three primary tasks. They first fetch sparse tiles from global memory to shared memory and reconstruct them in shared memory. And then they fetch dense tiles from scattered position in matrix B and store them to shared memory too. Well, before using the tensor cores to compute on those tiles, they first transfer those data from shared memory to registers and use tensor cores to compute on them. So TCGM has laid the work and demonstrated the potential of tensor cores for accelerating general purpose SPMM. However, we have identified that there exist several gaps that prevent TCGN from surpassing those highly optimized kernel parts based on kernel cores. So to address this, we conducted a thorough examination of TCGN SPMM from both algorithm and microarchitectural perspectives. Using a variety of real-world matrices, and we identified 5 major areas for improvements. One key issue is that the storage format used by TCGN consumes much more memory than the widely adopted CSR format. We know that the memory efficiency is critical for memory-bounded kernels, like especially SPMM. Additionally, we observed that the number of non-zero elements within the TC block in TCGN is relatively low, averaging about 15, indicating a significant amount of redundant computation. Furthermore, the number of exaggerated integer computation instructions significantly exceeds the number of actual tensor core computation instructions, that is the HMMA instructions. Most importantly, the utilization rate of the tensor core pipeline in the TCG-SpMM kernels is quite low, falling short that achieved by the TC-based GM operations. And we also analyzed the saturation time per streaming multiprocessor and found that the TCG-SpMM suffers from severe loading balance issues, which are highly dependent on the input matrix. And the specific reasons of all these gaps are detailed in our paper. Based on these observations, we developed DTC-SpMM, a comprehensive system that incorporates a range of targeted optimization techniques to fully harness the power of tensor cores. This system consists of 4 key components: the TCU catcher reordering modular, and the format transformation modular, and a high-performance runtime kernel, and a simulation-based selector. We accelerate these critical components by developing high-performance GPU kernels to reduce overheads. So as the foundation of the entire system, we designed a more efficient storage format called METCF. We leverage the characteristic that the coordinates of elements within the TC blocks do not exceed 256. So we use integers instead of 32-bit integers to record the indexes. And we do find that in some cases, or for some matrices, METCF format is more memory efficient than the CSR format, than the widely used CSR format. So to address the low density of non-zero elements in TC blocks, we introduced a novel 2-hierarchy clustering technique, that is the TCU catcher reordering. And the first hierarchy cluster rows in the sparse matrix with high J-car similarity into groups. And we limit the number of rows in per group to 16, which matches the height of TC blocks. And we believe that this tight limit can maximize the density of TC blocks. And the second hierarchy further clusters similar groups together to form a cluster of clusters. And we can enhance the L2 cache heap rates. The most critical component of the system is the high-performance runtime DTC-SpMM kernel. We implement our DTC-SpMM kernel with low-level PKS programming, and we introduced 3 novel techniques to improve the utilization rates of the TCU compute pipeline. Firstly, we propose a shared memory bypassing technique that enables us to store data from matrix B directly into registers, and we can enhance the memory access efficiency. And to utilize the more efficient vectorized memory access instructions, we introduce a register remapping method to ensure that the distribution of registers meets the requirements of TC computation. Well, we know that the registers follow restricted distributions among 32 threads in a work before using tensor cores to compute on them. Thus, we use register remapping to reorganize the distributions without online overheads. Additionally, we proposed a sparse double buffering method that overlaps the loading of the next sparse tile with the TC computation. We think this is the first time to apply double buffering to sparse tiles, and our smart double buffering can also be used to other SPMM implementations like Sparse. We designed a load balancer task division and deployed a simulation-based method based on a widely acknowledged thread block scheduling policy model to determine the best task division strategy for each input matrix. We utilize the concept of the mixed span to decide on the strategy without having to perform the SPMM computation. And for the experiments, we conducted experiments on two recent Ampere and Ada GPUs, and we compared our DTC-SpMM with the latest SPMM implementations, including both CUDA-core-based and Tensor core-based approaches. The results show that we achieved significant speedups on a variety of real-world matrices. And the blue bar is the performance we achieved, and the higher is the better. We also analyzed the results on the sparse matrices collection, which contains many real-world sparse matrices from various domains. We achieved remarkable speedups over the current state-of-the-art SPMM implementations, and we only suffered performance degradation on a very small percentage of matrices. And ablation study also confirmed the effectiveness of each of our proposed techniques and their combinations in enhancing the TCU pipeline utilization. And we also conducted a case study for GN training. SPMM has been regarded as the most important operation in graph convolution layers. So we integrate our DTC-SpMM into PyTorch and build a widely used two-layer GCN models. We name these models the DTC-GCN models. And we monitor the end-to-end gene training time on several real-world graphs. And on the different configurations, we set different dimensions. The results demonstrated that our DTC-SpMM can achieve considerable end-to-end model training speedups compared to the widely used frameworks like PyTorch Geometric and Graph Library, the DGL library. And we can also achieve speedups to compare with those recent proposed frameworks like the TCGN framework. And notably is the formal convolution overhead is relatively low compared to the entire training process because we use GPU kernels to accelerate the formal conversion overhead. And I think that's all for today. And thank you so much for listening. Please be free to ask any questions.
Thank you. Rubo, are you online? Yeah, you unmuted yourself. Thank you. Any questions? Yeah.
Hello, can you hear me? Or should I speak louder? Okay, sounds good. Erasmus from IUC. Interesting work. I wonder, in comparison with SPMM kernels in GPU that do not use the tensor cores, like GSPMM or adaptive sparse styling, those kernels typically face problems either because they reach the bandwidth roofline or because the threads in the GPU have imbalance. In my understanding, in order to get performance from the tensor cores, the bottleneck should shift to computation. So I'm asking, what kind of graphs did you evaluate on? Were they super dense?
Rubo, did you hear the question? We're not hearing you. I see you have unmuted. If you're talking, I'm not able to hear you. I see you unmuted. Are you talking? Is there a chat or anything? Yeah, he has unmuted, but I don't hear him. Yeah, we should. Sorry, we'll try to figure it out. Is venue or anyone? Oh, you're here. Okay, great. You can try to get yourself set up. Thank you. So the last session in this talk will be from Venue from University of Georgia. He'll be presenting his work on SOD square, which is statically optimizing.
Previous speaker can't take questions?
Yeah, unfortunately, no.
Yeah, that's not fair. Yeah, no problem. So.
Yeah, he has actually unmuted himself, but we can't hear him. He's online apparently, and he has unmuted himself, but there's some issue. Yeah, sorry about that. Yeah, so Venue will be presenting his work on statically optimizing dynamic deep neural network execution.
Yeah, thank you. So. Okay, yeah, we get it. Hello, everyone. I'm Wei, and I'm from University of Georgia. And I'm very happy to present our work SOD square, statically optimizing dynamic deep neural network execution. And this is a collaborative work between University of Georgia and William Mary. So in the previous neural network, we actually have the static neural network, which means it can only take static or the fixed input shape, fixed shape of the input, and also its execution is static as well. So in other words, we're not able to change the execution path for static neural network. So the benefits of the static neural network is definitely we have the fixed input shape. We can do the memory planning and execution planning offline. And also we can do some of the operator fusion because we already know the shape. So it is free to do the loop fusion as well. And however, more recently, we have seen a wide range of the network, which are dynamic neural network. So here we show 3 different examples. The left one is the routing network. In other words, we have some gating mechanism to control. And for some specific input, we can go through some simple execution paths. And in some cases, if the input is different, its value is different, then we can go to some complicated paths as well. So here we show we can either go to the left way or go to the right-hand side. And the second type is skip neural network. The skip neural network means we can actually selectively execute some node by some policy. For example, if we're executing this node, after that, our neural network will probably tell us, okay, the input is very simple, and we can skip the next node. Just to execute this one right after what we want to skip. So it can help us to save some execution or to save some computational cost. And the third type is actually more straightforward, which is dynamic shape. For example, the NLP model, like transformer, they can process any kind of input with different lengths, depends on the user's input. So the dynamic neural network have pros and cons. So for the pros, it is more adaptive. It has higher adaptiveness. It can process different situations, to execute different paths according to different input. For example, for the mixture of expert model. So you can select different experts to process your input. And it has higher representativeness as well. However, because we're not able to know its execution path statically, and we're also not able to know its input shape before we get executed. So in other words, we're not able to do the execution planning. We're not able to do the memory planning to get a memory allocation planning to get a minimum
memory fragmentation. And also, existing framework process this kind of workloads on the mobile device. They prefer the reinitialization for different input. In other words, if we get some different inference instance, like different input shape, we wanted to do the reinitialization to get the better execution planning or memory planning. However, this reinitialization is very expensive. And this table we show the how the reinitialization cost for both mobile CPU and mobile GPU. So here, this table we show the result for three model, the Euro, Conformer, and the Codebird. And this is the CPU execution latency, and the right-hand side is the GPU latency. And every latency, we have the schedule, allocation, and the inference. As you can see, especially for the GPU latency, the allocation for reinitialization cost, which is even 30 times over than the inference side. So in other words, the reinitialization is very expensive for dynamic neural network. And in this paper, we propose some specific optimization and propose a abstraction of operator type according to relationship among the input and output shapes. And also we propose we implemented a static analysis method, which we call it RDP analysis for propagating the shape and size of the in the dynamic neural network. And also we get a comprehensive set of static and dynamic optimization and achieve up to 7.9 times speed up compared to the Fusion, TVM, and MNN respectively. So this let's take a look at what is our high-level idea. So in this paper, we design a framework to accelerate the DNN execution. And the key idea is we found that different operators in the DNN computational graph, they have different dynamism from some certain degree. For example, in this slide, we show 4 different categories. One is the input shape determining output, which means the output is determined by the input shape only. For example, this node, as long as we know the shape to this shape node, we want its value, not only the shape. So this is the easiest one, the input shape determining output. Another one is the input shape determining output shape. In other words, as long as we know the input shape for a certain node or a certain operator, what we can get is the output shape only. We're not able to know its output value. So the convolution is a representative operator for this category. And there are some more complicated, the input shape and value determine output shape. So in this kind of category, the output shape is determined by the input shape and the input value. So in other words, as long as we really get into this node, otherwise we are not able to know its output shape. This is more complicated. And the last category is the execution determined. For example, as we introduced earlier, the MOE, the mixture of expert or the routing network, the only way we can know is we really executed this node, and then we will know which path we will go through. So this is execution determined. In other words, during the runtime, we can know this information. Otherwise, we are not able to get it. And here we show the more detailed classification for four of this category. The shape, this column shows the representative operator belongs to some specific category. For example, the convolution matrix unification, that belongs to the input shape determining output shape. And if loop or combine, their execution determines output. And after we get this information, what we can do is we can separate the operator by its shape and the value information. So basically, to do a memory planning or execution planning, one of the information is most important. That is the shape. As long as we know the shape for the specific operator, we can know how large the memory we need to hold this intermediate result, and also what is the computational size, and what is the latency expected to be executed for this certain operator. all of this information depends on the shape, but value is another factor because some operator is output shape is depends on the value. So as long as we get this information, we can use the rank and dimension propagation. We developed the rank and dimension propagation algorithm, and the detailed algorithm is in the paper. If you are interested in this algorithm, please refer to our paper. And the high-level idea is we developed a lattice analysis framework based on this rank and dimension propagation. The main purpose is we utilize the forward and backward paths. This is different to the model training, the forward and backward. And the forward means we go through for example here, this is a simple network. And in the forward path, as long as we know the shape for this S0, we can forward propagate it. And to see, because every operator, they have a shape function. If we know this, we know the input shape, we can get some information about its output shape. So in the forward path, for example, as long as we know the S0, we can propagate the information for S1 and S2, S3, and S4. However, in some cases, because the output shape depends on its value, so we still need to do a backward shape propagation to get more information. Like in this example, as long as we know the S4, we can get some idea or get some hints about what is the shape of S3 and S1, as well as S2 and S0. So after this forward propagation and backward shape propagation, we can collect almost all of the shape information, unless the operator that depends on some runtime value, the execution value. So this slide shows another example for the operator fusion. Because in traditional operator fusion or loop fusion, if we don't know the shape relationship between the input and output, it is very hard to generate the efficient code or even to fuse them together. For instance, here, if we don't know the I prime, J prime, K prime, the relationship between I prime, J prime, K prime to the I, J, K, it's hard to get these two for loop fused together because we don't know whether this I prime is I or not, right? And after our forward and the rank and dimension propagation, we can know what is the relationship between this I, J, and K, and I prime, J prime, and K prime. So we can fuse them together. And here is finally we show our evaluation. We evaluated our framework against MN, Onyx Runtime, TVM, and Nimble. And we also evaluated 10 different models, including generative models. And because this is a dynamic network, so we randomly sampled some input with different value and different shapes to get the execution. And all of the results are collected on the mobile device. And here, the first column shows this slide shows the end-to-end CPU memory evaluation. The first column shows 8 different models. And the full result is in our paper because of the limited space limitation for the size. And here, what we care about is the memory consumption. As you can see, the last 2 columns is the memory consumption by our framework, and other columns are from different frameworks. And dash means these models are not supported by the specific framework. As you can see, we can save up to 8.62 times memory compared to other framework, the TVM with Nimble extension. And compared to other Onyx Runtime and MNN, we can still save a lot of memory consumption as well. And another evaluation is about the latency evaluation. We compare the execution latency for different framework on different models. And the final conclusion is compared to the CPU, we can achieve up to 2.7 times speed up. And for the GPU, we can achieve up to 3.9 times speed up. We listed this as dash because the TVM with Nimble extension do not support GPU at the time of evaluation. So this is about our paper, and I'm happy to take any questions.
Thank you. Any questions? In your time slide, can you go on slide before? Can you clarify what is min and max for time? For memory, I can understand it's min and max during the execution, but what does min and max for
Latency
mean?
Yeah, this is a very good question. So basically, we didn't list the evaluation full evaluation setup in this slide. We selected 15 different input with different input shape. So the shape is different, then the final computational size is different. Right? The flops is different. Then the latency is different. Okay. Yeah. Thank you.
Yeah.
Thanks for the nice talk. Yeah, my question is that it sounds like your technique is not limited to mobile devices, right?
Yes.
Yeah, it can be used for all the platforms. So I was wondering what's the reason you evaluated them only on the smartphones?
Yeah, this is a very interesting question. So if you look at this slide, and what we found is on the as you can see on the CPU, for the CPU latency, the allocation is very, very fast. And on the desktop, actually the memory allocation is really, really fast as well. And what really motivate us mostly is the GPU, actually the initialization takes a lot of time. So that is why we choose the mobile device as our evaluation platform. And this framework is actually general to be applicable to other platforms as well. But just because the mobile device can expect better performance. Yeah. Okay. Thank you.
Okay. Thank you. Let's thank the speaker and all the speakers. Yeah, that ends this session. Thanks, everyone.
Thank you.